Today, after 13 years of having this event, we have a special guest, which I would like to introduce to all of you. It's President Bobby Robbins, President of the University of Arizona, who would like to just welcome you briefly.
Good evening, everyone. Joaquin, I have been hearing about this moment since I arrived in May, and first of all, thank you all for being here and supporting this incredible series. I think it's, people have told me this is one of three things: the Festival of Books, the Gem and Mineral Show, and this lecture series. The three biggest things in Tucson. And Stephen and I was trying to loosen him up over there because it's got to be pretty intimidating to come out here and try to get you all in 50 minutes to understand artificial intelligence and machine learning. But I'm hoping that we made a good enough hire. I don't know what the cross-section is of people who come to this event and those who attend athletic events, but I hope we made a good choice with the football coach, first of all. And you're okay with that. But we were both saying, okay, it's time, Joaquin. You've made it to the big time. Next year, you're going to have to do this in McHale, and you're going to fill up McHale because you're bigger than the basketball team. So congratulations on that. In all seriousness, Joaquin is I'm not going to say what I usually say, but he is one of the most talented, intelligent, charismatic people I've ever met in my entire life, and we're blessed to have him here at the University of Arizona, without question. So Stephen's going to tell you all about AI, machine learning. I've been talking about the fourth industrial revolution, which is the convergence of biological, digital, and physical science, which we're one of the greatest universities in the world around the physical sciences. So, one day in not too distant future, you'll learn over the next couple of weeks through this lecture series, you're going to be able to just take one of these things and take a picture of the mole on the back of your hand and say, Siri, is this a cancer? Yes, and she's going to say yes. And then there'll be a little thing that comes out and takes a biopsy and analyzes all this stuff. The last part is all contrived, of course, but the first part is real. It's happening now, and certainly happening in medical imaging around CT scanners and MRIs. GE, Philips, and Siemens are spending billions of dollars putting these algorithms together to be able to make diagnoses. So I'm going to try to make every one of these lectures because I am so excited about the topic. Joaquin, thank you for selecting this topic for this lecture series. Thank you all for supporting the university and for giving me a few minutes to say something. Congratulations.
Thank you, President Robbins. And as all of you know, this kind of operation doesn't come without financial costs. And I must thank those individuals and organizations that make it all happen. Tucson Electric Power, Ventana Medical Systems, and the UA Research and Discovery and Innovation program of the U of A are the title sponsors. Without them, this would really be a lesser event. And I also thank the underwriters, Accelerate Diagnostics, Arizona Daily Star, Canyon Ranch, Cox Communications, Galileo Circle, which are the individuals in our community that support the College of Science biannual contributions to fellowships and scholarships. Godat Design, all of the beautiful imagery that you've seen comes from them. Halualoa Companies, the Marshall Foundation, Wynn and Tebet Patent Law. Raytheon has been a great supporter since the beginning. Research Corporation for Science Advancement, and Tech Launch Arizona. If we could just have a round of applause for these folks. And as you know, for those of you that are now sort of the aficionados of this, part of the funding that comes from these entities goes to pay for high school and middle school teachers to take a course at the U of A, which allows them to be intimately involved with the curriculum that comes out of this, creating curriculum which will be novel so that they can take back to the community. So thanks very much for that as well. So now I have to introduce a speaker if I can get this done. So today's, before I introduce the speaker, there's going to be a short clip that actually tries in 3 minutes to describe where artificial intelligence and machine learning is going and where it has come from, so that you can fill the details with Stephen's talk. But you know, there's a lot of people out there, including Bill Gates and others, that argue that artificial intelligence is going to be the end of all. And I'm more with Kobourov, that says that it's mostly plain dumb stupidity that's going to do us in. So, but anyway, let's see the clip for a minute.
We are wondering what is happening to the world. Everything is changing.
The very idea of human being some sort of natural concept is really going to change.
Our bodies will be so high-tech, we won't be able to really distinguish between what's natural and what's artificial.
Inside our own heads is the most complex arrangement of matter in the known universe.
You might ask yourself, can we get to be superhumans?
The original Industrial Revolution was driven by the discovery that you could use steam engines to do all kinds of interesting things.
That was followed by additional revolutions for electricity and computers and communications technology. We're now in the early stages of the fourth Industrial Revolution, which is bringing together digital, physical, and biological systems.
One of the features of this fourth industrial revolution is that it doesn't change what we are doing, but it changes us.
We need a different economic model that will allow us to meet the basic needs of every human on the planet, and that will be focused not on growth per se, but on maximizing human well-being.
We have energy technologies that can power our civilization, but how do we get it and implement it at the scale we need at a price that people around the world can afford?
If we're able to do something to transform cities, to make them more efficient, then the impact can be huge.
We can use asset tracking, we can use IT, we can use 3D printing to decouple growth from the resource constraints we have.
The question of adding quality to quantity, it's really about a diverse, safe, healthy, and just world with clean air, clean water, clean energy.
Together we are fighting to preserve our fragile climate from irreversible damage and devastation of unthinkable proportions.
The prediction of 5 million jobs lost by 2020 to technology is serious, but the main question is, how will we define work? How will we share the wealth?
How can you have a doctor that really knows a lot about data? How can you have a biologist that knows about medicine?
We have to create a space that enables people to think freely, to think divergent thoughts, to think creative thoughts.
We really need new education or new training.
We're working with a World in Motion and First Robotics, trying to encourage students from 3rd grade all the way up through the end of high school to pursue science, math, and different technologies.
It's this ability of digital technology to change outcomes, to truly empower people that can create a more equitable growth.
Fourth Industrial Revolution has the potential to make inequalities visible and to make them less acceptable in the future.
I was the first person in the world to be able to voluntarily move my legs while stepping in a robot. A cure will be possible if enough of the right people have the will to make it happen.
We're seeing this incredibly exciting convergence of genome editing, DNA sequencing. Governments have a very important role to play in enabling the safe and effective use of technologies.
We need to take responsibility at every level of society to adapt to these technological challenges, which are redefining what it means to be completely embedded in this world.
Even though we have everyday problems we have to solve, we have to find a way to lay the foundations for the innovations of tomorrow.
So that's the promise of the fourth industrial revolution. And today, Stephen Kobourov will describe what actually really goes on in those machines that allow us to even think about the possibilities that were described. Stephen is a professor here in the computer science department. His bachelor's of science is in mathematics and computer sciences with a minor in classics from Dartmouth. He has a master's and PhD from Johns Hopkins. He's author of over 150 research publications in algorithms, information visualization, and computational geometry. 2006 Fulbright to help develop graduate programs in computer sciences at the University of Botswana, and in 2011 to 12 worked in Germany as a Humboldt Fellow. He spent a year in AT&T Research Labs, working in their information visualization group, and in 2015 he was a distinguished Fulbright chair position at Charles University in Prague. He plays the bass in the Department of Band and runs marathons, including the now defunct Mount Lemmon Marathon, touted as the world's toughest road marathon. Stephen, welcome.
Thank you, Dean Ruiz. Good evening. Thank you, Dean Ruiz and President Robbins, for making my first slide unnecessary. Let's go back in time. A long time ago, in a country far, far away, a mythical hero named Theseus was born. Theseus did the standard hero trials and tribulations. He slayed some monsters, founded the city of Athens, and traveled a lot by ship, which was all good because his father was the sea god Poseidon. As Theseus traveled by ship, his ship kept changing. He lost an oar here, a sail there, a few planks, a few oarmen. After a while, not a single piece of his ship remained, which led the philosophers in Athens to wonder. This ship became a standing example among the philosophers for the logical question of things that grow, one side holding that the ship remained the same and the other contending that it was not the same. How is this relevant and how is this related to the fourth industrial revolution, artificial intelligence and machine learning? A few years ago, Marvin Minsky, the founder of the Artificial Intelligence Lab at MIT, asked the question, will robots inherit the Earth? And his answer is yes and no. He says, yes, but they will be our children. And what he's thinking is similar to the ship of Theseus puzzle. What if we continue evolving and augmenting ourselves? An artificial joint over here, a cochlear implant over there, external memory devices like our phones, and maybe one day internal memory implants. Will it still be us? This is one very optimistic view of the future. Certainly not all subscribe to it. Here's the alternative. Will our cute little vacuum cleaners grow up to the Terminators of the science fiction movies? Well, scary artificial intelligence is something that keeps many of us awake at night, especially those who read science fiction movies, books, and watch science fiction movies. Is Skynet of the Terminator movies already active and plotting our demise? Are we living in the Matrix? The physicist Stephen Hawking is on the record as saying the development of full artificial intelligence could spell the end of the human race. And he's not alone. Elon Musk, the CEO of many high-tech companies such as SpaceX and Tesla, thinks that we should be very careful about artificial intelligence and that it could be the biggest existential threat. And Bill Gates is in the same camp. So, prediction is difficult, especially about the future. This could be attributed to Danish physicist Niels Bohr or Yogi Bear, depending on who you ask. A while back, Lord Kelvin, the president of the Royal Society, thought that X-rays are a hoax. We still use them today. No less than Albert Einstein considered that there's no indication that nuclear energy will ever be obtainable. And yet, 20% of the energy in the United States today is obtained from nuclear power plants. And Thomas Watson, the chairman of IBM, didn't see a market for more than 5 computers. I'm willing to bet that there's quite a few who carry more than 5 computers on your bodies right now. So, what is going on? Technology used to be understandable and simple. When my toaster breaks down, I could take my screwdriver, open it, repair the wire, and it works again. Today, technology is literally and figuratively a bunch of black boxes. Our phones, our laptops, and the algorithms that run them, Facebook, Google. Many of us wake up in the morning with an alarm from our smartwatch that is monitoring our sleep and selecting a light sleep cycle to wake us. Then music starts to play, which is selected by an algorithm that has learned what we like to listen to, not only in general, but also early in the morning. And then as we are sending our pre-coffee messages, autocorrection algorithms are repairing our typos. Spam filters have automatically removed most of the unpleasant messages we receive. Then we go in our cars, and our GPS devices try to guide us to work so as to avoid traffic jams. You come back at home, and Facebook has found a new friend you completely forgot about. Netflix recommends a movie that you're stunned that you like. So, Arthur C. Clarke, science fiction writer, said that any sufficiently advanced technology is indistinguishable from magic. And when it all works out, it does look like magic. But it's not magic. This is what I'll try to talk about tonight. It is not magic, but algorithms, programs, machines, and data that we have designed, implemented, and made into these black boxes. And in order to do this, in order to understand how these black boxes work, we need to look inside. And this can be intimidating because we'll be talking about strange terms such as artificial intelligence, machine learning, and algorithms. At the core of it all are the algorithms. And there's a saying, there's a difference between knowing the name of something and knowing something. I will try to go beyond the names of these things and into them so we can catch a glimpse of what is inside our black boxes. And it all starts with algorithms. The word could come from Latin, As Dean Ruiz mentioned, I studied classical studies, and Latin and Greek were among my subjects. The usual suspects for the origin of a word are Latin and Greek. And many of my students would agree that algorithms seem to be impersonal, cold, and painful. Many people noticed a certain correlation between the appearance of the word algorithms in our newspapers and media and the appearance of the internet, which led some people to conjecture that maybe our vice president had something to do with it. The consensus is that the word actually derives from the name of a 9th century Persian mathematician who we can also blame for algebra. So what is an algorithm? An algorithm is a step-by-step procedure for solving a problem. And very broadly, it's a recipe. And like many of us who have followed the recipe to its terrible conclusion, it can lead to disaster. As the joke on the right-hand side tries to illustrate, shampoo bottles that say lather, rinse, repeat give us an algorithm, and if you follow this algorithm, you fall into one of the classic computer science traps, the infinite loop. There cannot be a science talk that doesn't involve the physicist Richard Feynman, and this is relevant because Richard Feynman worked with computers, designed algorithms, and wrote programs for a company called Thinking Machines. And Feynman is credited for creating a meta-algorithm, an algorithm for all algorithms. And it's the problem-solving algorithm. And it goes like this. Write down the problem, think real hard, write down the solution. Now, there was a variant of this problem which was write down the problem, ask Feynman, write down the solution. But since Feynman is no longer with us, we're stuck with this variant. And at first, people see the ha-ha in the algorithm, and then they see the aha. This is beyond funny. There is some depth to this, as we'll hopefully find out as we talk more about algorithms. So, there will be a little bit of mathematics ahead, but I promise to keep it on a reasonable level. As every Hungarian child knows, 32 times 21 is 672. But an algorithm for multiplication is a recipe for multiplying any two numbers and getting the correct answers, not just 32 times 21. So we all learned how to multiply numbers in the standard US style. Write down the first number, write down the second number below, take the 1 from the second number multiplied by 32, take the 2 from the second number multiplied by 32, shift it 1 to the left, add column-wise, get the answer. But there's more than one way to multiply, so here's another one. This is my favorite multiplication algorithm, because it doesn't involve any multiplication at all. Make a grid with 32 by 21 cells and just add all the dots. Now, a side note, if the numbers were the same, if I was computing 32 times 32, this grid will be a square, which is why we say 32 times 32 is 32 squared. For those who are visual thinkers, the Japan-style multiplication may appeal to you. Take the number 32 and represent it as 3 lines in a group followed by 2 lines in a group. Take the number 21 and represent it as 2 lines in a group followed by 1 line. And now count the intersections. Okay, that's not quite right. let's look at some regions. The 3 times 2 gives us the hundredths. This is 6 hundredths. And in the middle, we have the combination of tens from the first number and ones from the second, and ones from the first and tens from the second, which gives us the 7. And at the end, we have the ones multiplied by the ones, which give us the 2. Isn't that amazing? One more, Russia-style multiplication. Instead of learning the entire multiplication table, which gave nightmares to many of us, how about we just learn to multiply by 2 and divide by 2? Take 32 times 21, multiply 32 by 2, divide 21 by 2. Do it again. Do it again. Do it again. Okay, what have we done? 512 is not the answer, because we didn't quite exactly divide by 2. So from time to time, there's these pairs of numbers that are exactly the same. 64 times 10 is the same as 128 times 5, so let's forget about one of them. Similarly, 256 times 2 is exactly 512 times 1. Let's forget about one of them. And now let's add the remaining numbers on the left. 32, 128, 512. Now this may look strange and weird, but in fact, this is the algorithm that our computers use to multiply. Why? Because we represent our numbers in binary notation, and multiplication by 2 and division by 2 are the easiest way to do this. I've been told that I cannot talk about algorithms without talking about sorting, because sorting appeals to most computer scientists who like to bring order out of chaos. Many of you perform sorting when you sort your cards or sort your mail. So I will illustrate just one algorithm for sorting, and once again, not just sorting these numbers in increasing order, but you can think of the sorting idea as applying to addresses, names, and numbers. So the idea is to take an input, figure out a sorting algorithm, and produce the output to the right. There's a very simple algorithm that people use when they sort cards. They pick the largest card, put it at the end, find the next one, put it at the end. This is not as easy for algorithms, for computers, so I'll describe a sillier algorithm, which is very easy to implement correctly so that our computers don't make mistakes. And it goes like this. Here's the numbers. Start looking at pairs from left to right. If you see a wrong order, repair it. 6 is greater than 1, flip it. 6 is less than 8, okay. 8 is greater than 7, flip it. 8 is greater than 2, flip it. 8 is greater than 4, flip it. Aha! The largest number bubbled to the top. Do it again. 5 is greater than 1, flip it. 5 is less than 6, 6 is less than 7. 7 is greater than 2, flip it. 7 is greater than 4. 7 bubbles to the top. Keep doing this over and over and over. It sounds very boring, but computers don't mind. Okay. Algorithms, examples of algorithms, many different kinds. Why so many different kinds? Why am I making you do math at 7:35 on a nice Monday evening? Because it's important to understand the underlying problem. When we learn just one way to solve a problem, perhaps we don't understand the full complexity of the actual problem. Why do we need so many cooking books? Why do we need so many recipes for chicken soup? The more we try, the more we understand about what's going on, and the better we are at actually solving the problem. So understanding the problem is fundamental. One of my favorite writers, Kurt Vonnegut, said that his principal objection to life is that it is too easy to make perfectly horrible mistakes. When solving problems, when we're designing algorithms and implementing them, it's even easier to make horrible mistakes. And when we do make such mistakes, you all hear about it. Y2K. It cost billions of dollars to fix. The Mars orbiter crashed due to two different groups one using metric units, meters and centimeters, the other using imperial units, feet and inches. And my favorite mistake, Gangnam Style, which broke YouTube because YouTube didn't anticipate that so many people would like to watch any movie, any video. I would like to point out that it is very easy to blame the algorithms, but we wrote the algorithms. And with that caveat, after mentioning Gangnam Style, I have to show you.
Open Gangnam Style. Gangnam Style. Open Gangnam Style. Gangnam Style. Open Gangnam Style.
This video has been seen more than 3 billion times. Now, when everything works out fine, when we understand the problem, when we implement the algorithm correctly, you don't hear about it. When Apollo 11 sent men on the moon, very few realized that behind this mission were hundreds and hundreds of algorithm designers, programmers who had to make this work. And in fact, the leader of the team was a woman named Margaret Hamilton. And nobody knew about this. And we're okay with that. When everything goes fine, we don't hear about the algorithm successes. Here's another example. When we sequenced the human genome, there was a lot of discussion about the biology, about the future, the engineering, but underneath it all were spectacular algorithms that were designed and implemented well. In fact, a University of Arizona professor in the computer science department, appropriately named Gene Myers, created one of the algorithms that sits behind the human genome process called the BLAST algorithm. So, understand the problem, think hard, implement it well. These are the 3 steps of the Feynman algorithm. And then everything is great. This is what people believed not so long ago. In about 118 years ago, the preeminent mathematician of the time posed a list of 23 questions, which he thought were the most important questions in mathematics. And one of them was the 10th question, which sounds very strange. I will read it and then translate it into English. Given an equation with any number of unknowns and with an integer coefficients, devise a process according to which it can be determined in a finite number of operations whether the equation has integer solutions. In English, it means devise an algorithm to solve equations, which is a very reasonable thing to ask. We need to solve equations in every field of science and technology, in physics, in chemistry, anywhere. So he was not asking something very unreasonable. And many of us remember, perhaps painfully, how to solve quadratic equations. There's a formula, you plug in some numbers, you get the answer. Hilbert was asking for a slightly more general question, not just one variable, but multiple variables. And people thought, indeed, this is a very important problem, let's solve it. And they tried, and they tried, and they tried. But as the saying goes, it's difficult to find the black cat in a dark room, especially when the cat is not there. It turns out that this problem, and many others, cannot be solved. We cannot design an algorithm, no matter how hard we work, to solve them. 2 famous people are associated with some of these results. Kurt Gödel is a mathematician, Alan Turing is a computer scientist, and independently they showed that there's not in fact just 1 or 2 problems, but infinitely many problems that we cannot solve. So remember the big picture. Take the problem, think hard, translate it into something that we can formalize, solve it, and Bob's your uncle. Not true anymore. So what do we do now? Even the problems that can be solved are not all equally nice, like sorting or multiplication. So let me give you an example of a problem, again, that is not at all very esoteric or strange. The traveling salesman problem. Imagine you're a traveling salesman who would like to visit all of the state capitals. And you would like to minimize the amount of distance you travel. Can we solve this problem? It turns out that this problem can be solved in finite amount of time by an extremely simple algorithm. Consider all possible routes. First visit city 1, then 2, then 3, then 4, and so on. Or first visit city 2, then 1, then 3, then 4. Evaluate all of them, pick the best. Sounds great. However, even for just 100 cities, we have to evaluate 10 to the power 156 different routes. And this number is greater than the number of the atoms in the universe. And one definition of a good algorithm is one that finishes while you're still alive. Okay, so now mathematicians and computer scientists faced a conundrum. What do we do now? Many problems cannot be solved efficiently, and many more problems cannot be solved at all. Well, we have to try something different. An example of something different are machine learning algorithms. So what is this different idea? Traditional algorithms provide solutions that are exact. 32 times 21 is 672, not about 600. But what if we're willing to tolerate about 600? Then we get to algorithms that give us good enough answers, which explains why computer science is the only industry where you can make billions of dollars making things that mostly work. There's a saying that goes, don't let the perfect be the enemy of the good. So good enough is better than nothing. If we want the exact solution for many problems, we cannot get it. So let's try to get something that's good enough. So what is the idea behind machine learning? Instead of designing the algorithm that takes us from the input to the output, we'll try to learn what the algorithm is that takes us from the input to the output. Let's look at many, many, many examples and try to guess what's going on underneath. Okay, this sounds a bit unclear. Let me give you an example. Imagine you have a series of input-output pairs that look like a picture of a cat and the word cat, a picture of a cat, the word cat, a picture of a dog, the word dog. Many, 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 many of them. Can we learn somehow to associate the thing on the left with the word cat when it's a cat and the thing on the left with the word dog when it's a dog? Or how about something that many of you actually use today? The input is a bunch of movies associated with a number that may correspond to how much you like the movie. This may come from my Netflix preferences because I tend to like science fiction, but not so much fantasy. So after many, many, many examples of input-output pairs, can we figure out when a new movie comes in whether I'll like it or not? So machine learning algorithms are different in that they are supposed to improve with experience. And this is based on using very fast computers, statistical analysis, and many, many, many examples. And this is, in fact, where big data comes in. And in a couple of weeks, Nirav Merchant is going to talk about the implications and applications of big data. But today, I will show you just a little bit. There's a saying that goes, give a man a fish, he'll eat for a day. Teach a man a fish, he'll eat for a lifetime. What if we give a machine a fish? I will show you a machine learning algorithm in action. The machine learning algorithm is going to try to figure out what I'm drawing, really what I am drawing with my mouse on my screen. I recorded it, and there's supposed to be a video in there, which hopefully works. And you will hear the machine guessing as I'm drawing. And I will be quiet while this is happening. So you can all try this if you enjoy it. It's called Quick Draw! Exclamation mark.
I see line, or ocean, or river, or string bean. Oh, I know, it's canoe. I see line, or arrow, or string bean, or seesaw. I see rake, or pliers. Oh, I know, it's bow tie. I see party hat, or triangle, or water, or pants. I see vase, or lock, or floor lamp, or umbrella, or hammer. I see house, or barn, or bucket, or satellite. Oh, I know, it's mushroom. I see seahorse, or arrow, or mountain, or stitches. Oh, I know, it's shark. I see stairs, or line, or keyboard, or bench, or pillow. I see sleeping bag, or pencil. Oh, I know, it's stereo. I see line, or diving board, or garden hose, or canoe. I see marker, or mouth, or pencil, or mouse, or bread. I see speedboat, or shark, or eye, or dolphin, or toothpaste. Oh, I know, it's fish.
Wasn't that cool? So now you learned that in addition to not being very good at playing the guitar, which is why I played the bass, I'm also not very good at drawing. How did this machine learning algorithm do what we just saw it do? This is how. 136,000 examples of mushrooms drawn by people like us. And 126,000 examples of fish, none of which looks like mine, by the way. So I will try to help you get a glimpse about what these machine learning algorithms are doing. They're finding patterns and trends and correlations. So for example, my fish looked very similar to the sharks, and my mushroom looked more like a party hat than a mushroom. So imagine having millions and millions of examples and then trying to arrange them in such a way, somehow, that more similar things are close to each other and more different things are far from each other. And then when a new one comes in, trying to place it. This is, on a very high level, what is going on. But before I can show you 5 million or 20 million fish and mushrooms, I'll start with something much simpler. Recall Morse code. A long time ago, in a galaxy far, far away, we used to send telegraphs by encoding letters with electrical symbols, dots and dashes, short and long. Many of us still recognize SOS, dot, 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 dash, 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 dot, dot, dot. And some of you may notice that Samuel Morse, the inventor of this, was an admirer of Ludwig van Beethoven, because the encoding for V, which is also 5 in Roman numerals, is dot, 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 dash. So when you send Morse code messages, it is possible to confuse the characters, because some are similar to each other. For example, if I send the letter A twice, dot, dash, 92% of the time people agree that it's the same thing that I send. If I send AB, dot, dash, dot, 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 only 4% of the time people think it is the same letter that I send. And what we get is a similarity matrix. And don't be afraid, this is tiny data. This is not big data. This is tiny, tiny, tiny data. But what is the idea? We want to group things that are similar close together and put things that are different far away. So this is what an algorithm will do with that data. And at first, we don't see anything. We didn't quite sort the numbers. We talked about sorting. Wouldn't it be nice if we sorted them? But if you look carefully, we kind of sorted them, but in at least two different dimensions. If you look from bottom to the top, we sorted them by the length of the encoding in Morse code. The single guys are on the bottom, and the 5 guys are on top. And in fact, if you squint and put your glasses on, you will see that we also sorted them in this dimension. The characters on the left are a bit more dotty, whereas the guys on the right are a bit more dashy. But there's more, right? It is more easy. The long encoded characters are more similar to each other. They're more easy to confuse, rather than the short ones that are not as easy to confuse. And this is useful for many things, but for example, error correction. If you receive a message where there's something clearly wrong, you can look for the most likely character to have been misinterpreted. But in particular, it's useful to illustrate what do we learn from the data. We cannot get the exact answers, but we can get some idea of what's going on. So let's try something slightly bigger. The post office scans our letters electronically. And one of the things that it extracts are the addresses and the zip codes. And this is a data set full of handwritten digits, 70,000 of them. And this shows you what the machine learning algorithm learns when it analyzes 70,000 digits. What do we see on top? The zeros seem to be easy to distinguish from anything else. But the 1s and the 7s are pretty close to each other. My 1s always look like 7s. And the 9s and the 7s are also close to each other. And as we can see, 8s and 5s can be confusing. So this is extremely useful for machine learning algorithms to, for example, figure out what zip code you want to send your letter to. But how about a problem, a real problem, one that people are willing to pay money for? Netflix offered $1 million to the team that can improve their recommender system. This was a while back, so don't try to win the $1 million. It was won already by a team at AT&T Research Labs. The team was called Bell Core, and it was named after two researchers at AT&T Bell Labs, Bob Bell on the left and Yehuda Koren on the right. Now, the data set that Netflix made available was quite large for its time. 20,000 movies, 500,000 viewers, and 100 million ratings. And the idea was, can we improve the recommendation system over what Netflix was already using as its in-house algorithm? The history is slightly entertaining. The data was released on the 2nd of October, and it took exactly 6 days for the first team to improve on the Netflix in-house algorithm. And it took about a year to get a certain amount of improvement over the algorithm, 8.4%. I joined AT&T in 2008, AT&T Research Labs, and talked with these guys, and they told me a somewhat entertaining story. When they wanted to participate in the challenge, the AT&T management told them that they shouldn't, because AT&T is not interested in recommendation business. What does AT&T have to recommend? Good decisions don't make good stories, bad decisions do. The next year, AT&T started to deliver television over cable to compete with companies who were delivering telephone service over cable. And very quickly, they amassed a data set which was even larger than the Netflix data set. And it was even harder because whereas Netflix provided us information about what movies people like and what movies they don't like, from the TV data set, we only had information about what people have watched. One of the scary things that come out of this data set is that on average, an AT&T Uverse subscriber had their TV on for 10 hours a day. But the idea was to apply the same principle. Let's look at the data and try to find correlations, patterns, and trends. And when I joined AT&T Labs, I tried to help them visualize the output. And you can see that the problem is similar to all the previous problems. I've invented these numbers here to illustrate a point. The information that we had is people who watch PBS NewsHour also tend to watch Antiques Roadshow, but not so much Iron Chef. On the other hand, people who watch Iron Chef also watch Chopped. These are cooking shows versus shows on PBS. So the data that we had looked like this. People who watch a particular show often watch this other show or don't watch this other show. And this was a table of size 37,000 by 37,000. So slightly larger than the Morse code example. But the idea is the same. We visualized what the machines learned with this map, which of course nobody can read, which is why I'll helpfully zoom in. On the top, very top, where the black box is, we discover a group of shows that are very much kids' shows. There's Disney's Mickey Mouse Clubhouse, there's Harry Potter. Okay, if we go all the way to the bottom, we discover home improvement shows on different channels with challenging and provocative names, such as Property Virgins and Desperate Landscapes. Right next to them is a region which we labeled Hungary, because it is mostly cooking shows, such as Chopped, Iron Chef, etc. The news got split into several different areas, and on the left, completely coincidentally, you have to take my word for it, on the left ended up shows such as CNN Newsroom, Anderson Cooper, Larry King Live. You can tell this is old data set. But also, if you look up, The Daily Show with Jon Stewart and The Colbert Report. Now, on the right, I swear completely coincidentally, we ended up with a disjoint group of people who watch Fox News Sunday with Chris Wallace, Fox and Friends, but also in the top left of the same group, Live from the Masters, Golf Central, Mad Money, and Fast Money. And of course, on top, in an island, separate from everybody else, is a group of shows that I bet you somebody can tell me what's the common theme. Barney and Friends, Sesame Street, Antiques Roadshow, NewsHour with Jim Lehrer. PBS. Okay, so what did we learn from the data? That there are some patterns and trends. For example, in the horizontal dimension, we seem to be capturing age. Certainly kids are not watching cooking shows and home renovation shows, and certainly not many adults are watching Harry Potter and Disney Mickey Mouse Clubhouse. But this was also useful to see how our recommendation algorithms are working. Are they doing the right job or not? So, a very important caveat. Did watching too much Fox News lead people to play golf? Or was CNN headline news the gateway to the Jon Stewart show? Because correlation does not imply causation, but this correlation is what machine learning algorithms pick on. And this is why we have to be careful for problems like this. When the hurricane approached Florida in September, prices shot through the roof. And the headline, not in the Daily Mail, but in an NPR, said, "Algorithms show no sympathy." The algorithms learned that people are willing to pay more money to get out of Florida. Turns out algorithms are racist. When an algorithm helps send you to prison. In 3 weeks, Jane Bambauer is going to talk about biases in our data. If you feed biased data in, biased results come out. There's a saying in computer science that goes garbage in, garbage out. So we made these algorithms, and we should be aware that these biases exist. So we went from algorithms to the new algorithms, and now we've reached AI. What is AI? Artificial intelligence technically is concerned with the theory and development of computer systems that are capable to perform tasks that we associate with human intelligence. John McCarthy coined this term, AI, in 1955, while he was at my alma mater, Dartmouth. Later on, he went to MIT and Stanford. And he thought that this was not the right term because it set the expectations too high and it doesn't really capture what we're talking about. Perhaps mimicking intelligence is more accurate. From the time of Icarus and Daedalus, going back to the ancient Greeks, people have tried to fly. There's many illustrations of Icarus and Daedalus with wings made out of feathers. Leonardo da Vinci drew winged machines. And in the end, we did build airplanes which have wings. But airplanes are not birds. Similarly, we've always wanted to build swimming machines. There's excellent swimming machines called fish and sharks. And if I draw them, they look exactly the same. But submarines, which is what we build, are different from fish and sharks. So artificial intelligence is neither artificial nor intelligent. It's different. And the best way that I have seen to describe what artificial intelligence is that it's an aspirational term. It reflects a goal. And the goalposts keep moving. Initially, people thought, what are the hardest things we can do? Playing chess is very hard. I bet you we cannot make a machine that plays chess. Well, Deep Blue was a machine built to play chess, and it beat the world champion Garry Kasparov. And then people said, but wait, what about Jeopardy? Jeopardy seems to be even harder than chess because you need to connect historical facts with trivia, with word play. Bet your machine cannot do that. Well, IBM Watson beat the Jeopardy champion. So currently, something that seems to be challenging for artificial intelligence is this. This is the state-of-the-art robots not too long ago in 2015, and they're having a hard time walking. But I have no doubt that very soon we will have machines that walk quite well. In fact, I have no doubt that we'll have machines that run quite well. I have no doubt that there will soon be a machine that can beat men in running. The Rome Marathon has a very nice motto. It says, "Coro ergo sum," which translated in English means, "I run, therefore I am." If this was the goal, I have no doubt we'll get there. But Descartes said, "Cogito ergo sum." I think, therefore I am, not I run, therefore I am. So, can our machines think? Will they turn into whole from 2001 Space Odyssey? This is a question that Alan Turing, my favorite computer scientist, asked in 1950, way before any machines were actually having the potential of thinking. And this is the first sentence in his essay called Computing Machinery and Intelligence. Can machines think? And he proposed several objections, and then he tried to address them one by one. For example, the God objection. Thinking is a function of a man's immortal soul. God has given an immortal soul to every man and woman, but not to any other animal or to machines. Hence, no animal or machine can think. Turing's answer is quite nice. Should we not believe that God has freedom to confer a soul on an elephant if he sees fit? Who are we to tell God what he can do? This is not the right objection to thinking machines. How about the head in the sand objection? The consequences of machines thinking would be too dreadful. Let's hope and believe that they cannot do so. His answer is just as relevant now as it was 68 years ago. This argument is not sufficiently substantial to require refutation. We should think about it, and this is why we have a lecture series on this topic at the University of Arizona. Ada Lovelace was another unsung hero of computer science. She is credited as the first programmer. She worked in the 1800s with Charles Babbage on his engine, and she designed the first algorithms and implemented them. And she is credited as saying, a machine has no pretensions to originate anything. It can do whatever we know how to order it to perform. A machine can never really do anything new. In the 20th century, Pablo Picasso summarized this objection by saying, computers are stupid. They only give you answers. But I will paraphrase a quote from our President Bill Clinton, who said, it depends on what your definition of the word is. It depends on what your definition of the word originate is. Some of the algorithms that we've talked about today challenge the question that machines cannot originate anything. So what did Turing actually write in his paper? I highly encourage you to read it. It's eminently readable 68 years later. He carefully, just like Marvin Minsky, dodges the question by saying, basically, intelligence is as intelligence does. So, along the way, in the same paper, he created something he called the imitation game, that many of you now know of as the Turing test. And so far, no machine has passed the Turing test. So I left one objection from the paper for the end. The argument from consciousness. Not until a machine can write a sonnet or compose a concerto because of thoughts and emotions felt, and not by the chance flow of symbols, could we agree that a machine equals brain. That is, not only write it, but know that it had written it. And this one is worth thinking about, and I hope Mihai Surdeianu will be able to tell us the answer next week. Thank you.